Welcome to the fifth lecture on the unit of electromagnetism. In the previous lectures, we have understood the different concepts of electromagnetism and were able to obtain four important laws or four important equations, which are the Gauss laws, the Faraday's law, and the modified Ampere's law. The Maxwell's equations basically is when you consider all these four together. So the first Maxwell's equation is the Gauss law of electrostatics, that is del dot E is equal to rho by epsilon naught, which means that the total electric field or the total flux within a volume is equal to the charge density divided by epsilon naught. Then you have the total magnetic flux enclosed as zero, that comes from the Gauss law of magnetism. Next, variation in magnetic field produces an EMF or an electric field, that is a Faraday's law. Variation of electric field and the summation of conduction current and the displacement current results into the magnetic field, that is from the modified Ampere's law. So all these four constitutes the Maxwell's equations of electromagnetism. Now let's apply these Maxwell's equations and obtain an expression for the speed of light. Let's start with the Faraday's law. So we have del cross E is equal to minus dou B by dou T. Let's take a curl for this equation on both left and the right sides. So it becomes del cross E is equal to minus dou by dou T of del cross B. Now we already know del cross B from the modified Ampere's law, that is mu naught J plus mu naught epsilon naught into dou E by dou T. So let's substitute for this on the right hand side. And let's also consider that the current flowing through as zero or the conduction current density as zero. We are going to consider that the current density due to the conduction current as zero. So we now get del cross E as minus dou by dou T of mu naught epsilon naught dou E by dou T. The term mu naught J will not exist because we have considered that the value of the conduction current density J as 0. Now we can apply vector identity to the left hand side, that is del cross E becomes del of del dot E minus del square E. That gets equated to the right hand side. So right hand side simplifies as minus mu naught epsilon naught, since they are constant you can take them out, and dou square E by dou T square. Now we need some value for del dot E, and del dot E obviously comes from the Gauss law for electrostatics, that is del dot E is equal to rho by epsilon naught. Let's assume that rho is 0, charge density is 0. So del dot E becomes 0. So our previous equation was del of del dot E minus del square E is equal to minus mu naught epsilon naught dou square E by dou T square. We applied the Gauss law, but we take an assumption that the charge density is 0. So del dot E becomes 0. So this equation simplifies as del square E is equal to mu naught epsilon naught into dou square E by dou T square. Or I can rewrite it as del square E minus mu naught epsilon naught into dou square E by dou T square is equal to 0, and let me denote it as equation number 1. This represents the wave equation for the electric field, due to the electric field, due to the movement of the electric field. In a similar manner, we can obtain the wave equation for the magnetic field, that is del square B minus mu naught epsilon naught dou square B by dou T square is equal to 0. So for this, what we need to do is we start with the modified Ampere's law and then apply the Faraday's law and obtain this particular equation, bringing in again the conditions of current density becoming 0. So let's denote this as equation 2. And these two equations 1 and 2 are actually going to represent the electromagnetic waves. So electric field, we are going, what we basically understand from this is that electric field has a wave equation, means electric field is going to be represented as a wave. You can represent electric field as a wave. In a similar way, you can represent magnetic field also as a wave. And these two equations 1 and 2 basically give the expression for the electromagnetic wave equations. Now, in a general form, I can consider a wave equation as del square y minus 1 by v square dou square y by dou t square equal to 0, where y is the displacement, v is the velocity of the wave. So, if I compare this general form of the equation with the previous equations 1 and 2, that's the electromagnetic wave equation for electric field and magnetic field, I will get that 1 by v square is 1 by mu naught epsilon naught, or v square is equal to mu naught into epsilon naught. Or you can get the velocity as square root of mu naught epsilon naught. Let's substitute the values for mu naught and epsilon naught. All these are very simple values, the basic values which you are already aware of. So let's do the substitution. And what you will get is the value as 3 into 10 power 8 meter per second. And this thing which you already know from your school level, that this is the value for the speed of the light, that is given by the letter C, denoted by the letter C. Speed of light in free space. So hence we have got the expression for the speed of light by making use of the Maxwell's equations. So basically what we did is we considered the different Maxwell's equations and we obtained the wave equations, electromagnetic wave equations, either in terms of the electric field or in terms of the magnetic field. Do a comparison with the general form for a wave equation, and you will get the value for the expression for the velocity of a wave, that becomes mu square root of mu naught epsilon naught, where mu naught is the permeability of free space, epsilon naught is the permittivity of free space. Substitute for the values of mu naught and epsilon naught and you will get the speed of the light in free space. So that's all in this lecture series about electromagnetism, the different concepts which we have discussed about. Thank you all. I hope you all have understood. Any queries, please leave in the comment section. Thank you.